Hello, good afternoon. I'd like to welcome everybody to our Dane Protects webinar series. Today's topic is to discuss expert application methods for power generation facility protection. I want to welcome everybody to the session. Looks like we have a really great turnout again. Thank you. I'd like to introduce myself, Mark Hendricks with Dane, and my colleague, Stephen Weber.
Hello, everybody, and welcome.
Thank you, Stephen. So our topic today, power protection at power generation facilities. We're covering the topics of risk analysis, design, product installation, quality control, and through final turnover book. Now, power generation facilities are very complex structures. In our photograph here, you can see just an example. They consist of a variety of structures with cooling towers, with combustion chambers, heat extraction systems, very extensive control systems. So there's a lot of high technology process that's going on these types of structures, especially the latest generation of combined cycle power generation facilities. So damage at power generation facilities takes a lot of forms. In this photograph, you can see there's actually a lightning protection system. It's a bonded system directly on the vents of these cooling structures, and you can see damage that gets incurred. This is possibly the result of lightning strike that actually hit the cable and caused the cable to be severed. And you see a variety of damage that looks like that. Things like air terminals mounted on lights where there's insufficient separation distance. Here you see examples where the cooling tower might have been struck itself, and it's caused the air terminals to become disconnected and basically falling off the structures, all the way down to the base where you see the earthing pigtails being severed. These are all possible types of damage that would be incurred from lightning strikes. Of course, there's other power generation facilities in the solar industry where it'll cause fire. You have direct strike energy directly into the bypass diodes and converter combiner boxes. Wind turbine power generation facilities, of course, very, very exposed type of environment with these tall structures and the extensive collection area. Here you see causing a very expensive fire on complete destruction of a type of a power generation asset. The damage can take the form of much more subtle damage on circuit boards and, of course, wiring systems that would cause the complete failure of a extensive wiring and interconnecting cable systems. You see a lot of damage to instrumentation systems, everything from blown up components to damage on circuit boards. You see damage to communication wiring. You'll see damage to power system wiring, and this can be particularly hard to troubleshoot and expensive to replace because it'll cause punctures in the wiring system that might require an extensive recabling of the wiring and power control systems. You'll see lots of damage to the communication wiring systems. It's really important to pay attention to not just the power and the high voltage cabling systems, but also to the power over Ethernet and low voltage communication systems. So the challenges at a power generation facility are particularly complicated because they're large systems with a lot of interconnected systems. You have damage from direct strike where it can strike directly into some of the buildings in a power generation plant. But you see that you have a large collection area, and you have extensive systems of power and earthing systems and communication I/O control systems. And this direct strike damage can cause a lot of ground swell. So you'll see in the earthing, this is a really good illustration showing an interconnected mesh earthing system. And so a strike on one end can actually induce ground potential rise all throughout the the power system and the information technology systems at a site. And that's in conjunction with indirect strikes at a power plant, where it can strike in the ground nearby, also causing that ground swell, that ground potential rise. It can also strike the power feed and the high voltage power lines coming in and out of the system. And so you have that problem where it's an extremely large collection area. And that really leads to the discussion about bonding and equipotential bonding to control these ground potential rise. So that large collection area also imparts itself in the risk calculation. So in the IEC 62305 system of lightning protection standards, what we see is it starts with an evaluation of your risk. And a power plant has a high degree of risk. It's a large structure. It's a large interconnected structure. It has very valuable power generation transformer systems, transformers themselves that will have very long lead times, and high value transformer type power generation systems. The risk of direct strike is high, as is the cost of downtime and repair. So when we look at the risk analysis, we always want to focus on necessary and sufficient measures. We don't want to go overboard, but you need to pay a lot of attention. You'll have structures that have EX zone, explosive zones, and you'll have different levels of occupancy at the control systems, at the administration buildings on these sites. So what we see in a example like this is that you can select enough of a lightning protection system, an LPL class 3, that reduces the risk below the tolerable threshold. But you can also be a little bit overboard if you select an LPL 1 type system. And this is, again, it's a matter of controlling the risk enough to be below the threshold, but not necessarily go overboard, because that will reflect itself in the cost of the system, both in the grounding means, the air terminals, and in SPD selection. So if you select the necessary and sufficient measures, you can control the risk and not become overly expensive. And that's reflected in the LPL class. So if you have something that looks like an explosive environment at a power plant with lots of explosive gases, then of course you want to pay much more attention to risk control. So you'll manage these high energy wrath of God strikes, but you'll also manage the low strike, because you want to account for more of the strike incidents. If you have something like a steel building and the contents are not particularly valuable, then you can tolerate more risk, and you can tolerate a LPL 3 or even LPL 4 type system where you're accommodating a narrower range of lightning strike incidents. And so a chart like this shows you the high levels of lightning and also the low levels of lightning. And that low level of lightning is what's important when we're discussing the rolling sphere. And so what we know about the propagation of lightning is it's the movement of charge in the atmosphere, and it provokes an electric field, and that electric field pulls step leaders. It essentially provokes step leaders to jump, and especially at that final striking distance. And what we understand about lightning propagation is that the current, that lightning strike energy that we just looked at, the current is what is the function of the radius of that potential strike. And so if you're closer to the charge, you'll provoke a shorter spike, and a lower lightning strike energy will lead to a smaller step leader. And what we see is that's reflected in the rolling sphere. So here we see a power generation facility with all those complicated cooling towers, the combustion stacks, the heat exchange, and the electric switch yard where the transformers are going to be located, of course. But what we see illustrated is that the smaller sphere is what's associated with the LPL1, and a larger sphere is what's associated with a less stringent LPL4. So depending on your risk, you will select the lightning protection level, and that will lead you to the selection of that sphere. And then you can design the air terminal placement. So what we have illustrated here is that theoretical coverage model that shows you that all of the structures underneath the air terminals are protected. And depending on the rolling sphere that you use, you can generate a coverage that is sufficient for that power generation facility. So the elements of lightning protection. This is where we actually want to, once we've decided what LPL level, now we can determine the air termination, the down conductor system, the earthing system, separation distances, and lightning equipotential bonding. And by selection of the LPL class, now we can design the system for the air terminal placement, the density of and the design of the earthing system, and of course the selection of surge protection measures. And so these are all dependent on that risk analysis. So start at your risk. Now you can start to apply the lightning protection elements. And you need to pay attention to all 5 of these elements. If you ignore some of them, what you'll see is more high risk of lightning side flash into an unprotected system. So this is where we start to apply all those aspects. You have a structure, in this case it's a cooling tower, and we know that these are very important for power generation. The cooling tower is what cools, of course, the water as part of the heat transfer cycle. So power generation is directly proportional to the amount of cooling that you can apply in a combined cycle plant. So we take a look at a structure like this, and we estimate the lightning, the spacing of the lightning air terminals, and from that, we can calculate the separation distance. So in an illustration like this, we see the initial calculation of separation distance. Then we can apply the actual intended design. And so here, the next illustration that you see is the evolution of the design. Now we're applying the actual air terminals onto the system, and we're overlaying those air terminals onto the light poles that that our customer might allow us to use. And so this gives us a really good target for where we're going to actually apply our air terminals. And then we overlay that with the grounding pigtails so that we know that the routing of the cables that will be acceptable for the customer. The customer doesn't want to have exposed cables for trip hazards across the deck of these cooling towers. And so we'll target to use an isolated conductor in the suitable cable trays that are on these systems. And so this is an illustration showing where the customer's cable trays that will run the motors and the earthing system and the control systems for all these turbofans as part of the cooling. And off to the left, we can see that this all has to be coordinated so that the down conductors on such a large structure come down onto the pigtails that are going to be on the earthing system around it. And so here you see an earthing system mesh as part of the interconnected structure that's buried in the ground. And then the pigtails emerge from the soil, and that's where we want to have our down conductor to bond into the earthing system. So here's a nice illustration of the calculated coverage. This is what the theoretical coverage of that lightning protection system will provide, and then an actual photograph of the finished system. And it's a little hard to see in this photograph, but you can see the air terminals are actually mounted on the light poles because the customer doesn't want us to apply a lot of extra poles and things across their structure. We want to be efficient, and we want to use the structure's natural light poles as part of our air terminals. And that leads you to the coverage model that you can achieve with such a design. And so what's nice is you get a really good correlation in your mind's eye of the air termination, the coverage model, and then how that will actually be achieved on the site. this is what that might look like on the deck of that cooling tower. And what's very nice about this photograph is that you can see it's a clean application. We're not applying the air terminals onto the plastic cowling of the structure. We're applying the air terminals onto the light poles that are already there on the site. And we're using an isolated air terminals, down conductor and air termination system, so that we avoid side flash into the cable tray and motor control wiring. Because you recall that the turbofan, the cooling of this provided by this cooling tower, is going to be directly proportional to the power generation at the plant. So this is a really nice set of illustrations showing those coverage models over these complex structures at such a power generation plant. And you have a really nice rendering showing the air termination rods over the structures, like the heat recovery systems, where we're actually generating the electric generators are inside these buildings. So these are all delicate structures, and especially the highly exposed high voltage step-up transformers that feed the actual power grid. So in illustrations like this, you get a really good feeling for the coverage model calculation and the coverage you can achieve from your air terminal placement. And what's nice about an illustration like this is you can see what it looks like underneath the zone of protection, what you would achieve and what you would enjoy if you were underneath this structure at the time of a lightning storm. So this is what that coverage model almost looks like, a blanket of protection. Of course, it's the calculated result of the rolling sphere coverage. So this is what you would achieve by being underneath such a structure. So earthing, we had a couple of really nice images of what that extensive grid looks like. So the soil resistivity gives you an indication of how you can apply your earthing system. So when we did our risk analysis for that structure, we can determine if it's a high risk, then we'll need a more stringent class of protection. If you have a more stringent class of protection, you have more detailed analysis of your earthing system. So the higher, the more control of risk, for instance, at an explosive environment, you'll need a higher class, the class 1, which would then tell you on a chart like this that you'll need more earthing measures. And that's a really good leader to what you see in a large-scale power generation plant. You have an extensive earthing system. Up in the upper left corner of this diagram, you can see this is what the interconnected mesh looks like throughout the whole plant. In the lower left, you see the actual touch voltage of that electric grid. And a very thorough grid as applied like this gives you a very good control of your earthing system. And then we have a little bit of a zoomed in illustration where you can see the large mesh that's across this plant, and then what looked like ring grid, like that type B earthing ring around each of these structures. And so this is part of your entire lightning protection system. So we talked about the air terminals, we talked about the down conductor systems, and of course you have to have that all connected to the earthing grid. This is what we see as a final result on that type of typical plant. We can inspect using those clamp-on meter methods where you can actually determine that the impedance at each of those pigtails is suitable and gives you a very low impedance connection to that large earthing grid. And so what that measurement system allows you to do is to inspect the pigtail connection to tell you that the buried connection and the above grade connection are both suitably bonded and in proper working condition, so that the customer has a very strong and a very clean impression of the earthing system that's actually all buried. And what you can get from the data from an inspection system like that is it'll show you where the problems are. If you're measuring .062 and .029 around the perimeter of a building at its pigtails, and then you find a pigtail connection that's orders of magnitude higher, that tells you that the buried connection has a problem. And that's what's really nice about meters of this type, that it's essentially an active ping. It actually injects a ping into the system, almost like a sonar, and then it listens for that connection. And it tells you that it's a well-installed loop. And again, what it's helping you do is it's helping you interpret the buried connections. You can see that there's a above grade connection, but you don't get to see the buried connections. And this gives the customer a very good indication that the buried system is suitable for his application. So that leads us to the next pillars of protection, the equipotential bonding and the surge protection. So here we have a diagram for power generation at a solar plant. And what's important about this is that you can see that you'll have SPDs applied on the high power DC collection at the actual string inverters and at the solar panels, but you'll also have surge protection applied on the data collection. The data network is just as important on these types of power generation facilities. You have to monitor all the various processes to make sure that the power plant is running efficiently. Solar power generation facilities have their set of challenges. Combined cycle generation also has a very high degree of challenges. And so what we can do is look at the entire power plant distribution, the low voltage and medium voltage distribution systems, and we can use that to apply proper surge protection measures. And what we learned from things like the Sandy hurricanes and Fujikawa disasters is that the backup generator systems are extremely important at a power generation facility. So the backup generation, the transfer switch associated with that backup generator, these are all extremely important aspects at a power generation plant that we need to make sure have proper surge protection measures installed. So surge protection applications at the various motor control systems. Here we see that this is surge protection at the vibration sensors on those motors at that cooling tower. These are all very critical applications. You want to control and have surge protection measures on the flow meters and the flow transmitters out at the site. And you also have to have surge protection back at the cabinet. We see in the standards that wire runs of anything more than 10 meters are going to have a very strong suggestion to imply surge protection measures at both ends. And so this is a really good set of photographs that show you to apply surge protection both at the sensitive victim, right at the point of use, and then back at the DCS control cabinets. Of course, you have all of the processes being controlled at the central control rooms. And so these are all very delicate, low voltage control systems that have to have surge protection measures applied. You have bulletproof protection at both ends. As I mentioned, the IEC standards dictate that surge protection devices should be installed if there's a longer run than 10 meters. And of course, on a very large power generation facility, you'll have extensive runs of data collection and CAN bus control systems. And these are distributed networks that span the entire plant. And so it's very important to have surge protection devices installed on both ends. This is a typical photograph of what you might see distributed around the power generation plant, near pumps, near the areas that are very highly exposed around the plant. And you'll see the recommendations for both type 1 and type 2 surge protection devices. Now, these are IEC type 1, which are rated to withstand that high ground potential rise that you'll see at these extensive power generation facilities. Grounding, bonding, and protection. This all goes together. If you can't bond your power wires, you have to protect the power wires. And that controls the voltage across the panel. So things like, these are the types of elements you're looking for. Things like these bonding wires across the doors so that the door doesn't have a voltage rise or left behind. The whole point about grounding and bonding is that everything is at one equipotential voltage, so that if there is a lightning strike nearby that causes a groundswell, everything rises together and falls together like a bird on a wire. It won't experience a high voltage. And that's what the surge protection does for you, is it controls that voltage. So all the more reason that you want to make sure that your surge protection devices are installed at both ends, both at the critical flow meters and back at the marshalling cabinets. Power over Ethernet. We're seeing more and more types of devices that are high exposed routers, sensitive cameras, switches, and controllers that are spread around the power plant. And what we see is that these power over Ethernet devices need to be protected at both ends. Again, out at the security cameras or out at the power over Ethernet appliance, and then back inside the cabinet at the switch and the routers to protect both ends. You'll see widely distributed CAN bus systems scattered throughout the plant, and these are applications where you want to have the surge protection devices out in the field, and of course back at the marshalling control cabinets. So at a power generation facility, that's an excellent opportunity to pay close attention to the zone that you're operating in. So the application of surge protection devices and the application of grounding and bonding measures lets you build a more and more controlled lightning protection zone. So something that might be an exposed power line coming into the building might be considered a type 1, and then where that particular power line or data control line comes into the final control room would be considered your more sensitive lightning protection zone. So it's a way of applying protection measures to create layers of protection so that you're more robust. And in this diagram, you can see all your pillars of protection. You have your air terminals, you have your down conductor system, you have your earthing grid, you have bonding measures throughout the plant, and then you have surge protection measures that give you that complete control of the pillars of protection. You don't want to leave any of these measures disregarded. You could have side flash, you could have problems with your bonding where a cabinet isn't bonded, and then you'll have uncontrolled voltage rises. And that's the whole point. We're trying to control and divert the lightning currents and then give yourself these protected zones of coverage. So when we're conducting these types of projects, these are very complicated, extensive projects. We take a very careful look at the grounding. We help design the ground field. We can calculate the earthing measures that have to be installed. We take a very careful look at the lightning protection rolling sphere coverage calculations around the plant to make sure that all of the structures fall within a protection that might be offered by the actual lightning rods. What's very effective about the IEC measures is it allows you to take advantage of the taller structures that are adjacent to a lower victim, and you can enjoy the coverage offered by those structures. We take a very careful look at the surge protection. We follow through with all the construction, engineering, drafting. As part of our projects, we take a very close look at the bill of materials, project management, and logistics. We offer lots of services for site installation, site training. We take a really close look at the site inspection and then give the customer the long-term maintenance plans. These power generation facilities are going to be in operation for decades, and the intent is that the customer has a very clear understanding of what was installed, and that they have a very clear maintenance and inspection plan to watch out for things that we saw early in the presentation. These broken pigtails, these broken lightning rods that aren't giving the customer any value. In our projects, we take a very careful look at the project compliance and quality control. It's directly built into the IEC standard. It allows us to do quality control and project management and project compliance from the very early design stage through the installation and then final inspection. And then what we can offer the customer is those ground bond measurements to show that the lightning protection system is actually properly installed and that it will give them the coverage that they need for these high value assets. As part of our final compliance, we offer the final turnover book inspections. We can work with UL, we can work with IEC certified inspections, and this gives the customer the full compliance that they need on their project sites. So that concludes the material that we have covered today. I'd like to see if we have any questions. Stephen, do we have any questions that have come in from our viewers today?
Hi, Mark. Yes, we did receive a few questions, not a lot. The first question addresses the clamp-on measurements that you've illustrated in the presentation. It's the person asks, can we use these clamp-on measurements to assess if the earth electrode is 10 ohms or less as recommended in the 62305 standard?
So what the clamp-on meter shows you is that it's measuring a low impedance loop from the buried portion through a loop back to the exposed pigtail that we're measuring. It's a little bit confounding because what's happening is you're seeing the entire ground field. You're not actually measuring the impedance of the connection of that earth rod into the soil. Those are actually best conducted using the follow potential methods with something like the brand Mager or Fluke offers some very effective measuring equipment. Stephen, I'm not sure if you have some other points that you'd like to add to talk about the measurement of an individual rod relative to the soil, and that's where the 10 ohm connection comes from.
Yes, I just want to mention, if we look at the general requirements of earth termination systems in the standard, remember that it mentions there that when we deal with lightning current, high frequency behavior, the shape and dimension of the earth termination system is the most important criteria. So in other words, they give us a 10 ohm recommendation, but from a viewpoint of lightning protection, we just need to make sure that we comply with a single integrated earth termination system that is the preference. And we know from simulations that on these power fields that they most likely will be less than 10 ohms if we do a follow potential method here. But they comply with the dimensions and they comply with the shape requirements, and thereby we will know that the dispersion of lightning current will be really good into the soil, and we have touch and step potentials that are acceptable. So yes, I agree with you, Mark. The clamp-on just measures loops, and you can't use it for that purpose unless you're going to be doing it for overhead power lines or so. You can use these clamp-ons for those type of measurements of individual earth rods in overhead power lines, but not really in a power generation facility in that way.
Yeah, and this is an excellent discussion that we could take offline with individual customer engineers that have want to discuss that in greater detail of what's the process to follow to actually assure that you're getting a 10 ohm system, because it does start with the follow potential and then the design of your earthing system based on that soil resistivity, and that's how you can assure that each rod contributes to the 10 ohm final result. That's excellent. Excellent question.
And then we have a question on these power generating facilities. We normally have tall structures. how does the IEC methodology for lightning protection address tall structures?
Yeah, Stephen, I might let you handle that one because you do a lot of our lightning protection calculations.
Yes, yes. So on the stacks that we design, where we design the lightning protection systems for, these are generally lower than 60 meters. And we would do the entire rolling sphere calculation, including the stacks, and make sure that they are protected. But if we look at what the requirements are in standard, if a structure is actually less than 60 meters tall, the standard actually mentions that the probability of strikes to the vertical sides of these structures is really low, that they do not need to be considered. But we do the rolling sphere for the roof and all the horizontal protrusions and stuff like that around these structures to make sure that they are protected. And then, of course, if these tall structures are higher than 60 meters in height, we can generally do an air termination system design that would protect the upper part. Standard says the topmost 20% of the height of these structures, and make sure that especially the points and corners and edges and those types of things of this tall structure is protected should a strike come from above. But the risk is generally lower for the percentage of flashes that we could that we can expect from coming from the sides. But in the case of these power generating facilities, structures, these stacks are not generally higher than 60 meters. So we would do, and if they are, we will do a protection scheme that would address the assessed risk that we see there.
Yeah, that's a really good point. And of course, that's really the intent of the air terminal placement, is that it's a big, tall steel structure may not actually explode if it's struck by lightning, but you don't want the lightning strike to attach randomly, because then it's going to get into the lighting and the instrumentation systems that are attached to these towers. So the whole point is to divert it safely into the steel of the structure, allow that steel to be the natural down conductor, and then divert it safely into earth. So remember, it's always about giving it a safe attachment point. Okay.
Yes,
excellent.
Then we have a question. We have a few that just came in recently. You mentioned that the IEC system allows you to take advantage of the height of taller structures. This is true for all standards based on rolling sphere method. What is the difference?
The difference. Well, what we see and it might be more important to point it out that in a UL inspection for a master label, they look at each building on its own as it stands alone. And even though there may be structures around it, the difficulty that UL addresses is that they don't know what's going to happen over time. So they assume that each structure has to stand on its own. So it may not be necessarily different that we can account for the structure next to it. It's that it's in the final inspections that they really pay attention to, that each structure has its own resilient system.
Then
okay.
clamp on and other low frequency meters cannot measure impedance. Why? They are measuring resistance. Why do you infer they are providing impedance values?
The clamp-on meters measuring resistance. That's correct.
Yes.
And the inference is that it's a low impedance connection to the soil. Yes, because we're looking at that loop and we're using that essentially it's a 5 kilohertz measurement. When it does the ping, it's at about 5 kilohertz. And so it's using that ping to show you that you have a loop. And that's the inference that we have a good connection into the larger ring.
Yes, and I mean, that's the important part. That's what we want to measure. It's exactly, we want to measure that loop, make sure that pigtail is connected, the down conductor is properly connected to the grounding system, and make sure that the lightning current can dissipate properly to the grounding system. That's what's achieved by using these clamp-on measurements. Then For design of an air termination system, one rod to the other rod for the rolling sphere, we can select other rod placement distance. Reduce separation distance in total distance to other rod. I actually, it's very difficult to understand what is being asked in this question.
We might have to take that one offline because we'll answer all these questions in writing separately in addition. So that one might be better off taking it offline and make sure we understand the actual intent.
I just like to address this last question before we finish up. The question is about using the natural steelwork of the facility as part of the lightning protection system. Mark, I'll just go ahead and make the first comments on this question. Yes, most of the designs that we perform for power generating facilities, if the specific area that's not that's assessed for protection does not really include critical equipment or does not house a lot of personnel, we can use the natural steelwork as down conductors for that section. And the only requirements that we have there is that the air termination system is steel installed and bonded properly to the natural steelwork of the structure, and that the natural steelwork of the structure complies with the requirements as it is in the standard. In other words, the electrical continuity of the steelwork from the air termination system to the earth termination system, as well as the minimum thickness requirements, so that we make sure that we don't get excessive heating of the structure, and there's no there won't be any melting or heating, like I said, of the natural steelwork. Mark, anything you'd like to add?
No, I think that definitely addresses the point, is that if as long as it's thick enough, it won't cause undue heating and rupture.
Yes, one thing to also mention is that the natural components of a facility can also be used as natural air termination. There's also a table 3 in the standard that also addresses the minimum thicknesses for these type of natural air termination systems. And but we need to take into consideration that if using these systems as natural air termination systems, you can get a direct strike on these structures. And if you don't comply with these requirements, you can get hot spots or even puncture or penetration of the lightning current. And that's why we also like to install the air termination system and bond that to the natural steelwork. That just lifts the coverage a bit higher and provides a point of attachment. And we make sure that that point of attachment is an air termination rod that has been tested to make sure that it can handle that initial charge and energy when the lightning is connected to it. And then we'll make sure of the electrical continuity for the natural steelwork in those type of settings. If it's a high critical area, like a motor control room or a concentration of electronics in some shed, there we go for methods where we can keep lightning current separate with, like you mentioned, Mark, an isolated lightning protection system with HVI, or a system that just maintains that calculated separation distance away.
Okay, great. I really appreciate everybody's attendance and the attention on our session today. Please look forward to additional webinars in our protection series in the coming weeks. And thank you for everybody's participation. Have a great day.